Okay, this will be the final video lecture in the series, what with the exam coming out on May 28th, which is only in a couple of days, depending on when you see this. In this final session, we'll be going through the last 3 exercises in the computer lab exam from last year. So, if we look at the first of these 3 exercises, here in exercise M5, we are given a list of reactions that represent a simple or minimalistic metabolic model with representation of glycolysis, TCA cycle, and oxidative phosphorylation, as well as a biomass function. And we are asked to write these reactions into a COBRA model structure and determine maximal growth rate with biomass as the objective function. So, yeah, let's just start by doing that. So here we have our little MATLAB session with COBRA already up and running. I'm just going to readjust the windows here a little bit so we can see both our model and what we type at the same time. So first, we want to just initialize our model. COBRA itself has already been initialized, so we can do model equals create. It should be create create model, I think, yes. Model equals create model. Let's just create it as a blank model. So here, this is just an original model structure. It has nothing in it, or it has certain fields, like reactions field, the stoichiometric matrix, and so on, but these are all empty. And so we're going to fill it with reactions one by one. So to do that, we can use the add reaction function. So we'll do model equals add reaction model, and then we want to give the ID for our new reaction. So let's start from the top. Let's write that R1, and then we will write in a reaction formula, which is a keyword that allows us to specify the formula of the reaction in the following string. And so the reaction formula for our reaction 1 is just a bidirectional exchange of glucose, which is formulated in this way. And now we see that we have added one reaction. It has a lower and upper bound of 9,000 and plus 1,000 respectively. That is not quite in line with what we have here, but we will change that later. And yeah, it has one metabolite, and that is it so far. Let's move on to the next one. So what we can do then is we just use the same function, model R2, still reaction formula, and here we do O2 bidirectional into nothing. Close parentheses. And we see now we have 2 reactions, 2 metabolites, which gives a 2 times 2 stoichiometric matrix, and things look reasonably sane. The important thing to keep in mind here is that is the use of spaces in the reaction formula. Essentially, that a space separates both a metabolite from the next, and so for instance O2 is treated as one metabolite because O and 2 are joined. There is no space in between them. This isn't too relevant now, but in a few reactions we'll see why this is important to keep track of. So we want now to add the third reaction. Well, R3, we can keep this reaction formula, and this is just a unidirectional secretion of acetate. So we'll write it like this. Now on to R4. This is where it becomes important to remember how this reaction formula syntax expects the input. So here we have glucose space plus 2 space NAD. Spaces, because if we were to have these without spaces, if say we were to write something like this, GLC plus 2 NAD, then this would then Cobra would just assume that this is one entire metabolite called GLC2 plus or GLC plus 2 NAD, and that is not what we want. So it's important to keep the spaces in. So here, GLC space plus 2 plus space 2 space NAD space plus. I'm going to stop calling out the spaces now. I hope the point is clear enough. Turns into 2 pyruvate plus 2 NADH plus 2 ATP. That is our reaction 4. Reusing this. This should not be R3, it should be R5. And then we want to add, yes, R5, which is 2 NAD plus pyruvate plus OAA turns into 2 NADH plus AKG. R6. That will be 2 NAD plus ADP, again remembering the spaces, plus FAD turns into 2 NADH plus ATP plus OAA plus FADH2. And here, since the 2 is actually part of the metabolite, you see here, then we process the we have them as a single string without a space in the middle. Very well. Then R7. Consists of 6 O2 plus 34 ADP plus 10 NADH plus 2 FADH2 turns into 10 NAD plus 34 ADP plus 2 FAD. Almost there. Now we're adding R8, which is 1 pyruvate plus NADH to AC plus NAD. And lastly, we want to add our biomass, which is model, we will call this one actually biomass, and then reaction formula again, 600 ATP turns into 600 ADP, again with all the spaces. Okay, so now we have our reactions in place. Now we could try to optimize this now. And we would get no growth because we are not quite done yet with building our model. The first thing is, as we told that we would come back to later, we need to set the reaction bounds. So if you look at our model here, we see that all our lower bounds are plus 1000 for all our original reactions, or for all our reactions, and then minus 1000 for R1 and R2, since these were specified as reversible. Meanwhile, the remainder, R3 through biomass, have a lower bound of 0 because they are set as irreversible. So let's change those to fit with what we want. These that are unspecified can be kept as 0 because the 0 is implied by directionality of the model, and an upper bound of 1000 should again be valid. Since these reactions here are balanced, a low limit on these LB and UB relative to the boundaries on the internal fluxes should effectively limit the internal fluxes. We still have to specify these boundaries for numerical reasons, but we want them to effectively not have any impact. We don't want the bounds on internal reactions to actually be limiting on our model. So let's change our boundaries. We call the model exchange reaction bounds model, and then we will say R1 0. No, that's not right. We want minus 10 L, and that has set our R1 to be minus 10. Let's do the same for R2. Just have there maybe that. We see that our LB changes as it should, and then we want to do the same thing but for the upper bounds. So then we just remove the minus and set AU here. There we go. Do that for R1, for R2, and for R3. Now our bounds are set as they should be. What we can do also is we can actually just double check that the mets are correct, that we don't have anything here that's not an actual metabolite, which would be maybe what we had if we made a typing error in typing in our models. We see GLC, that's glucose, that's something we do have. O2 is fine, that's also something we do have. Acetate, something we have. NAD, ADP, pyruvate, NADH, ATP, all good so far. OAA, that's fine. AKG is fine. FAD is also something we have, and FADH2 is also something we have. So all our metabolites here are good. If suddenly we had something like, say, pyruvates plus, which is not a thing, and it would that if we had something here that said like after 6 that was pyruvate plus or instead of pyruvate, then we wouldn't have known we made a typing error. So this looks pretty good so far. The last thing we need to do before we actually try to optimize this model is to set the objective. Because we see here that our C vector is just all zeros. We haven't given this an objective yet. And now we know that in models.reactions, it's reaction 9, that is the biomass, and that's the objective. So I'm just going to do a little shortcut here and just say model.C9 equals 1. Why isn't this? Oh, is it? Right, this is MATLAB and not Python, so you need to use parentheses to index elements. But yes, now we have our C is 1 for the 9th element, corresponding to the biomass reaction, and so the C vector should be quite accurate. Let's now try to optimize this. Let's expand this a little bit so we can see better what we get. We see that the value of the objective function here is 0.12222. And that is a reasonable growth for these parameters that we've given. So let's just type that in. We find, actually let me just keep so that the window stays above others, so we can keep that up while we tab back into the main window. So we find an optimal or maximal growth rate of 0.122, and then millimole per gram dry weight. Right, that's normally what the unit is, but that's not too important right now. So now the second step of this exercise is finding the reactions that are essential. So let's do that. Let's do a let's call it reaction KO equals single reaction deletion model. Here we go. Okay, so we see that we find a varying span here. Now, of course, when we're talking about essential genes and reactions, we need to decide what counts as that. And what we see here is that we have no deletions that have 0 impacts. All of them have at least some impact. Some are clearly essential. This one here, corresponding to R1, our glucose uptake. R4 is also 0, and of course the biomass will be 0 if we delete that. And so, of course, whatever standard we use, these will have to be included. While the others, that depends. I would say that if you were to insist that reaction 3 here, which is the acetate one, and reaction 8, 0.86 is a decent growth. Calling these genes or these reactions essential is a bit of a stretch. Meanwhile, for the rest here, they could be included or maybe not. But let's just describe a little bit what we have here. So we can say we find that reactions R1, R3, and R8 are, let's call it wholly essential. Let's see if I can, yeah, keep it like this. Maybe I can actually try to use the browser window in a little bit of a more efficient way as well. Okay, R1, yeah, R1, R3, and R8 are wholly essential, as the cell is incapable of growing without them. Why is that the case? Well, we see that R1 is our glucose uptake. That's our carbon source. And without this, we have no carbon source for our model at all. There is no alternate source from the environment of carbon. Similarly, we see that the glucose, once it's taken up, it's converted into pyruvate by reaction 4. And there is no other reaction that uses glucose. So if we were to disable reaction 4, then that is functionally the same as knocking out reaction 1, because it only has one way to go. And in fact, R1 and R4 would be strictly coupled, since they are the only they're the only outlets for each other. And the requirement that the glucose metabolite is balanced requires that these fluxes match each other. And if you knock out R4, there is no way for carbon, first of all, to be taken up, since there's nothing else to use it on, and then there's of course no other way of creating or of generating ATP from any other reaction, because they are missing their carbon source as well. And then of course the biomass is going to be essential. Now if we actually stop here and look a little bit at it, so our biomass function here is very simple. It's just turning ATP into ADP. So it's essentially a way of saying, is this model capable of generating ATP? That is what we're asking for. So, and what we see is that the only ones that are strictly necessary are these three. And yeah, we see that R4 R4 generates a bit of ATP in itself. And it also creates, and it turns some NAD into NADH and glucose into pyruvate. Now, if we were to just have R1, R4, and biomass in our model, our model wouldn't grow, because we would have an unbalanced production of pyruvate and of NADH that we wouldn't be able to do anything about. And we also wouldn't be able to create the NAD and ADP that we need to actually create this ATP in the first. Or actually, the ADP we would create, because that is created by the biomass function, but we wouldn't be able to create any of this NAD that is used. So let's look at the rest of our model here a little bit. We see that, so our first criteria here is that we need to do something with our pyruvate. We need to process it away somehow. And we have two ways of doing that. Either we can take the pyruvate and NADH together, turn it into acetate plus NAD, and then chuck that acetate out through R3. So that's one pathway we have of balancing this out. And in fact, if we were to have just add then R8 and R3 to our mix, then that is those 5 reactions would be able to grow. And this actually corresponds to what we see here with reaction 3 and reaction 8. These have the same impact on, or deleting these has the same impact, which is often an indication that these are strictly coupled reactions and that they follow each other in the metabolic pathway. And we see that, yes, indeed, the acetate is only produced by R8 and then chucked out by R3. So that would be in itself valid. But if we were to knock out R8 or R3, we see that our model here can still grow at actually a pretty decent rate, at 85%. And in fact, we see that another way of recycling pyruvate and also regenerating NAD is by using these pathways here. So, for instance, we can take oxygen in here, and then if we also manage to create FADH somehow, then we can regenerate NAD from NADH. And this FADH2 is actually produced by reaction R6, which in turn depends on R5 to produce the AKG it needs. But so essentially R5 through R7, these represent a separate aerobic pathway that is able to recycle pyruvate and NADH, and so balance really R4, which is what we strictly need to create any amount, or to convert our glucose into something useful. Now, incidentally, if we look at R5 through R7, we also see that this pathway generates quite a bit of ATP on the side, and so if in fact we see R5 through R7 correspond to these growth rates here, which is also coupled with our oxygen uptake, and these are quite critical. This aerobic pathway generates a lot of ATP and is also a very efficient way of recycling the outputs from R4. And so we could, if you want to, consider these as essential, but strictly speaking, we do have an alternative for them in the anaerobic pathway here, R8 and R3. That with just those alone, we could actually produce some ATP just at a very reduced rate. So let's just write down this in something of a useful format. So this is because our model needs a carbon source in order to generate the ATP needed for biomass production, with glucose as our only source. R1 is essential. R4 is the only reaction that can process this glucose into other useful metabolites. Of course, the biomass, also this R8 is not wholly essential. This is supposed to end the biomass reaction. The biomass reaction being essential is a matter of course. Now, let's return a little bit to what we said. We see that once that R4 can run as long as the model has some way of recycling the its byproducts, and the model has two choices for this. One aerobic pathway, so let's say R2, because we do need oxygen uptake for that. R2, R5, R6, and R7, and one anaerobic pathway, R3, R8, that secretes acetate. either of these being present is enough to allow the model to grow, but removing either has some effect on growth, with the aerobic, with knockout of the aerobic pathway having a more pronounced effect. This is a more thorough answer than really would be expected in such a question, but yes, this is more or less a summary of what's being asked. Okay, let us now move over to question 6. So here we're asked to compute a phenotype phase plane. So let's do that with a range of 20 and 50 points for, this is quite poorly specified, but for the glucose and oxygen uptakes specifically. So let's do this. Phenotype phase plane. We'll do model R1 and R2. Since we're not specifying anything else, typically phenotype phase plane will be carbon source versus oxygen source. So that's R1 and R2 here. And then we need to actually specify the number of points. If we type here help phenotype phase plane, let's pull this down a little bit. We see that it takes inputs, control reactions, number of points, which is essentially how many points we want to try, and then the range of fluxes that we're giving in. So let's do that. Phenotype phase plane model R1 R2. Let's take 100 as just a number we're inventing out of nowhere. 20 and 50, since that is what we're being asked about here. Colon, just so we don't get tons of zeros. Now this of course takes a little time, and we're requesting quite a few points here, but this takes quite a long time even for what is a very minimalistic model. So of course if you were to try to do this with a larger model, it would take quite a bit more time. But this is nothing that we can't just suffer our way through here and now. Now, for some reason I was a little bit worried here, since I am running MATLAB on a remote machine. I was worried that the rendering of the figures wouldn't be perfect. So actually, let's stop this here, because we want to be able to use this. There we go. Okay, it took a little while. Again, the problems of running things on a remote machine. But let's get our scales up and running. Now this phenotype phase plane is a bit peculiar. But what we're going to be using mostly here are our shadow prices here. And what we see is that in both cases they are positive in this band. Meanwhile, here we have just zero growth. So this is actually where phenotype phase planes can be a bit deceptive, and this is something we're going to be very much talking about in the next exercise as well. But these sides we see here are not actually really phases of their own. That's just because MATLAB, when it computes a phenotype phase plane, will create just a set of coordinates, and then we'll draw lines between neighboring points. And so a set of lines between neighboring points will draw out a surface. That doesn't mean that that surface actually exists. This is an abrupt transition here, as we see with our phenotype phase planes, that there's really only 3 phases here. There's no transition here. This transition is instantaneous. And so we see that on our blue phases here correspond to these flat regions in our phenotype phase planes. And these flat regions are have zero growth, so they are infeasible. Meanwhile, in the middle here, we have just one region with the same sign, positive, on the shadow price. And that means that we have a dual substrate limitation. So we find 3 phases. And technically we're not asking for infeasible here. One double substrate limited in the middle, the only region where growth is possible, and 2 and let's say 1 infeasible on either side of this double substrate limited. It's double substrate limited because they are both non-zero at the same time. If it were to be single substrate limited, one of these shadow prices would be 0 within the band, which they're not. And if it was futile, then at least one of them would be negative, which is also what we don't find. So that's why we just have this one phase here, and it's double substrate limited. Now, the double, onto B. Oops, almost deleted there. Thank God for the undo function. Now, the line of optimality, as a reminder from the lecture, is essentially the phase boundary where the carbon is oxidized as much as possible and used as efficiently as it can be. And the way we identify that is that we can choose one fixed value for our carbon uptake, and so let's say, and that's R1. So we just choose one vertical line here at any point of the scale, and then we will draw it up, and then we will find where we find the highest growth. And this would actually be maybe a little bit easier if you look on this here, which right now is not very willing to turn. But we see that since we are in this double substrate limitation, oh, I have just ruined it somewhat more. Anyhow, yeah, this should be a reasonable illustrative angle. So what we see here is that if we say we fix R1 at 5, then we have an increasing slope along the whole line. So increasing the oxygen uptake will bring us towards line of optimality, as long as it gives us, essentially we want to find this. If we look at this from above here, we want to follow this line from 5 until we find the highest growth on that line. And if we now try to spin this back to normal, we see that highest point corresponds to the upper line of this double substrate limited region. So let's write that out. We say the line of optimality corresponds to the edge of or to the phase edge where a given amount of carbon uptake leads to the highest growth. Since our only feasible phase is double substrate limited, this corresponds to the upper edge shown in the shadow price plot given by Cobra. So that is to this upper edge here. a way we could specify this as an answer is we could just give one coordinate on it. So we can say that, for instance, it would be 5 and let's say about 30. That could maybe 1 point on this line is R1 equals 5, R2 equals, well, let's say approximately equals 30. Okay, so let's close this down. And now let's have a look at exercise C. So we want to do the flux variability analysis with the biomass reaction fixed at 90% of the wild type optimal growth rate. We also want to compare against 100%. So let's just do FVA 90 equals flux variability model, and then 90, that is the set argument that will give us like the acceptable relative flux for our flux variability, or relative optimum. Actually, we need to call something. Let's call it FVA. Oop, wrong. FVA 90. Let's call it L, and FVA 90 U, because we want to have both an upper and lower bound for the flux variability. So this is what we get here. Yeah, this is correct. And then let's do the same for FVA for 100, and then come back to them and just generate both and then look at them afterwards. Okay. So maybe we can just look at them directly here at any given time. Or now let's pull this up and maybe we can get to see them all at once. So what we see here is if we require 100 FVA 100L, FVA 100U, our upper and lower bounds are essentially the same. And that is because we have the flexibility in our model essentially comes from that we have two alternate pathways. We have this anaerobic pathway and we have this aerobic pathway. And they have varying efficiencies. And so if shifting anything away from one into the other will have a very dramatic effect, or it won't have a very dramatic effect, but it will have some effect on maximal growth. If the most optimal usage involves a quite specific balance, but there is some redundancy, right? We have two parallel pathways that can sort of sacrifice, or that can be shifted off against each other at some sacrifice of efficiency. And so if we allow ourselves to drop down to 90% efficiency, we get these bounds here. We have, for uptake rates of, for instance, carbon uptake of minus 6.6 and an oxygen uptake of 10. Those are both valid. We see our oxygen uptake in either case will actually have to be quite high. Oxygen is our limiting factor here. But if we're to use the less efficient anaerobic pathway, we can to some extent make up for that by uptaking more carbon. In fact, and what we're limited by in this case is if we go for anaerobic is not the uptake of carbon, but we see here that's the secretion of acetate. That's actually our limitation. If we go here, the fact that there is an upper bound of 10 on secretion of acetate is not quite realistic, but it's something that's been included in this exercise to make the results somewhat more interesting. But yes, essentially what we see here is that if we allow a drop down to 90, we get a very substantial, a very wide span essentially in what are considered permissible fluxes, because you have the anaerobic pathway that can pick up for any deviation in the aerobic pathway and so on. This disappears if we want to be fully strict, because there is on the growth, because there is some loss of efficiency. So we find that with for FVA with biomass fixed at 100%, we have no variation or no difference between the upper and lower bounds given by FVA. For FBA, for biomass fixed at 90%, we find that let's try to put this aside so we can see everything at once. We find that most reactions can span, or we find that if we look here in detail, let's describe this a little bit more detail. We see that R2, which is oxygen, and then reactions 4 through 7, which are our aerobic pathways, they have pretty small spans, like from 2.9 to 3.3. That's not a very wide span, but it is some. So we can find that the optimum, or that the aerobic pathway has a reasonably small span in permissible fluxes given by FVA, while if we look here at the anaerobic pathway, which is R3 here from 2 to 10, and R8, which also 2.6 to 10, while the aerobic pathway has a much bigger span. We also see that, and this same applies to carbon as well. We have a decent span in the just initial carbon uptake of R1 and R4 here, right? These have about a factor 2 change. So, this is because we have two alternate pathways, one of which is somewhat less efficient than the other. This gives us a degenerate solution for the flux distribution, but at the cost of some efficiency if we push more flux through the anaerobic pathway. So yeah, that is roughly what we have. Okay, moving on to the 7th and last question, or 3rd for today, if you want to look at it that way. So we want to do a knockout of reaction R8, and then essentially redo the analysis from the previous exercise. So let's do that first. Let's make a duplicate model this time. So we'll call it model KO since we knock out reaction 8, and then we'll do remove reactions from model, and we'll remove R8. since we are going to be doing phenotype phase planes and so on, we're not going to do just a single reaction deletion, because that will just give us a relative growth rate. That's not what we're asking for here. What we want to do here is we want to create a copy of the model with R8 removed, and then we're going to do separate analysis from it. So here, this is model KO with R8 removed. Okay, so let's do the phenotype phase plane. Let's just call it the same, use the same calls for it, but with model KO as our argument. Now this is going to take us a little minute to create again. So let's just be somewhat patient with that. Okay, now it's finished. Now we just need to wait for my remote Xorg connection to render this, which is probably going to take a handful of seconds more. And already here we're starting to see something is weird. Let's concentrate a little bit more on this. On the actual phenotype phase plane itself, because what we're getting here is essentially a bunch of spikes. Similarly here with our shadow prices, just along a bunch of spikes. And this is where I have to point out that this is misleading, and the exercise is deliberately meant for it to be. Because a real phenotype phase plane will never look like this. This is not what a phenotype phase plane can look like. There's a variety of reasons for that. In fact, what's going on here is MATLAB is acting up on us, and or the restrictions of Cobra and MATLAB are coming into play. Because as we talked about earlier, what Cobra does is that it chooses, or it creates a bunch of individual points, right? This is not a surface, this is a set of points. And then it computes optimal solutions and so on for all of these points. And what we see here is that these spikes, they draw out a line. And these lines, these correspond to a set of feasible fluxes. And if we were to draw this like infinitely well resolved with an infinite number of points, this line here would actually be continuous. We would not have all these like spikes one after the others. What we would have is we would have two infeasible regions on either side, and then a very large, and then a very abrupt sort of just sheet, like one-dimensional plane, but limited, or two-dimensional plane, but limited in extent, that follows these lines. And this is because we have, let's go back at our model here, by deleting R8, we have knocked out our anaerobic pathway. All we have now is our aerobic pathway, and this aerobic pathway is consists of a chain of reactions that are all strictly coupled to each other, and that means that all our fluxes, since we just have essentially a single chain of reactions that are going one after the other, all our fluxes are perfectly locked with each other, which means that and that extends to R1 and R2. And so we can only have a feasible solution to our model if R1 and R2 are in that exact proportion. And as it happens, these points here, a few of them will add up. So let's say here we have three. Suppose we have a point here that the order is 3 to 1. So here we would have 6 and 2. I think actually 6 and 1 is, so it's 6 to 1. So this point 6, 1, then reaction 1 and reaction 2, their relative flux is within this exact feasible ratio. But as we set our points here, everything in between here isn't going to be exactly at a 1:6 ratio, because we might be adding 0.1 in each direction for each step. And in doing that, we are going to fall just slightly outside that acceptable ratio, and our fluxes will no longer be feasible. Just keep in mind, this is meant to be a tricky exercise. There's a reason why it is the last on the exam. And the purpose of this is to show how numerical errors are absolutely something that can happen when you do this kind of model. Don't have blind faith in what comes out. If the results that come out don't make sense, try to figure out why they do. And that is essentially what's going on here. The numerical limitations, that the fact that only a very few, like when we're doing these discrete, like pixelated points, only very few of them will fall within that exact span. Now, if we realize this, we can actually extrapolate in our minds what the phenotype phase plane will be here. And in fact, the phenotype phase plane here will consist of, again, two unfeasible phases, as we had earlier. And instead of having a more wide band with sort of an abrupt cliff on each side, we have a very narrow band, essentially so that it's narrowed to a plane, or a line, if we just look at the top of it, which is actually what we should be. And our phenotype, our double substrate limited phase, is in fact not a plane, but a line. Calling it double substrate limited is both sort of misleading, but also the only accurate way of representing it, in that the only way we can increase biomass production is, in this case, is by increasing both the oxygen and the carbon uptake at a fixed rate. Merely increasing one won't have any effect. Well, in most ordinary and realistic, double substrate limited, only increasing one would be beneficial. You would get more effect from increasing the uptake of both carbon and oxygen, but either one would have an effect. Here you need to actually increase both at the same time to have an effect. So it's a very fringe case which falls a little bit outside of normal scenarios, but that is what it is. Of course, this line that we have becomes the line of optimality, because it is the only region of our phenotype phase plane that allows for any form of growth. So we obtain a plot showing a sequence of spikes along a line. This is due to a numerical error. With the elimination of the anaerobic pathway, only the aerobic pathway remains, since our model is now a line. Caps lock is not being lenient to me. Is now a line, in the sense that if you were to draw a flux map of this, you just get a sequence of arrows one after the other. All our fluxes are coupled, which means that all feasible solutions require a fixed, let's say, ratio between our different fluxes. Due to the way Cobra MATLAB phenotype phase spaces sample the flux ranges for R1 and R2, all points where these do not fall, where these do not coincide perfectly according to the 6-to-1 ratio, are infeasible. However, and we can say since intermediate points between the spikes are rounded off to the nearest pixel, so to speak. So, for instance, if we say consider 6-to-1, 1/6 being valid, then if the next point is 1.01, 6.01, that won't be, that point will not be feasible. And then that next one would be actually 1.01, 6.06, but if our sampling actually is, let's say, something like this, then we're actually not going to catch these points. The ones that actually, where we find common multiples, that corresponds to our spikes. However, knowing this, we can resonate, or I don't know if that's the word. We can reason ourselves into how the phenotype phase plane should actually look. A single or two unfeasible phases as before, with a single line, feasible line in between, representing a form of dual substrate limited phase space. Again, this exercise, I will admit, is quite tricky, and it is intended to be. But it's, even if it might be hard to grasp the exact mechanisms of what's going on, the main lesson to take away from this is the notion of, like, if only you notice that this isn't right, this is not how it's supposed to be, even if you can't quite figure out the amount, like the actual problem within the bounds of within the time constraints of the exam, merely just noticing that, no, this isn't right, something is wrong here, I shouldn't blindly trust the numerical results I get from my model, you're coming a long way in coming with a correct answer to the exercise. That has to be said. So moving on to B, our last part exercise, and now let's just repeat the FVA analysis we did previously, and we'll do it with the 90% growth this time. We're not asked to do it with 100, so let's just do that. Let's call it FVA 90L and FVA 90U, and then we call it, yeah, actually I need to add in KO because we don't want to over add our numbers from earlier. Okay, so this is what we get from 90 KO, and what we see here is that where we without the deletion in the previous exercise, with by setting just the 90% growth, we had a pretty substantial span in the flux variability of quite a few fluxes. Now we see that the difference between the lower and upper bounds for the FVA solution is actually quite consistently 10%. And those 10% correspond to the 10% leeway we've given in the biomass objective. Because, again, all our fluxes now are strictly coupled. There is no redundancy. So all this variation gives here is just a homogeneous downregulation of a single pathway. And since there is no redundancy where we can trade off one pathway for another but at a reduced rate of efficiency, now suddenly, since that is no longer an option, we lose this flexibility in flux variability that we had from before. So yeah, I think there's not that much more than that to be said. So we find some variability or some difference between the upper and lower bounds given by FVA, but the ratio between the upper or the lower and upper bound is 0.9 for all reactions. This corresponds to the permissible reduction given as an argument to the FVA function. Since we removed or knocked out the anaerobic pathway, we no longer have the option of readjusting fluxes from the more efficient anaerobic pathway to the from the more efficient aerobic pathway to the less efficient anaerobic pathway, removing the source of the variability found in let's just call it M6. So yeah, that is the last question for this exam. And with that, not the last question, or the last part of the last video that will be posted through this class. Thank you.